Hello everyone and welcome to today's live broadcast, Overcoming the Challenges in New European Pharmacopoeia, chapter for WFI production, presented by Tony Harrison, Senior Marketing Manager at Beckman Coulter. I'm Susie Valdez of LabRoots and I'll be your moderator for today's event. We're delighted to bring you this educational web seminar presented by LabRoots and sponsored by Beckman Coulter. Before we begin, I'd like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time during the presentation. Just click on the green Q&A button located at the lower left of your presentation window. Type your questions into the box that appear on the screen. We'll answer as many questions as we have time for at the end of the presentation. Also, notice that you're viewing this presentation in a slide window. To enlarge that window, just click on the screen icon located on the lower right. If you have any trouble seeing or hearing this presentation, click on the support button at the top right of the presentation window or use that Q&A button and let us know you're having a problem. One reminder that toward the end of the presentation, audience members will have the opportunity to answer a poll. We really encourage you to participate. Without further ado, I'd like to introduce our presenter, Tony Harrison. Mr. Harrison held the convenorship of ISO Working Group revising ISO 14698, Section 1 and 2 for microbial control in clean rooms and was the UK subject matter expert to the ISO Working Group who issued the 2015 revised version of the ISO 14644, Section 1 and 2 documents for cleanroom classification at the heart of the aseptic manufacturing chapters of both the European GMP and the USA cGMP documents. Tony holds a bachelor degree in electrical and electronic engineering and is employed by Beckman Coulter Life Sciences as a senior marketing manager. Experienced in water system TOC, conductivity, and ozone analysis, and cleanroom environmental monitoring as well as particle characterization, Tony has spent the last 15 years in applied metrology for the pharmaceutical and healthcare manufacturing industries. Prior to that, he worked for companies providing process control automation solutions for manufacturing industries. Tony was the joint editor on the ISPE Guide to Ozone Sanitation of Pharmaceutical Water Systems and was also the chief editor of the PHSS Best Practice Guide for Clean Room Monitoring. Tony is a well-known international speaker and has provided educational seminars on TOC, liquid particle counting, ozone sanitation for water systems, and clean room monitoring in the UK, France, Italy, India, Malaysia, China, USA, Scandinavia, Ireland, Hungary, Switzerland, Indonesia, and many other countries across the world. I'd now like to welcome Mr. Harrison. Welcome.
Thank you very much for that introduction. I appreciate that. Hello, everybody. My name is Tony Harrison. Today I'm going to talk about the increasing importance of monitoring for total organic carbon and conductivity, particularly in the light of the recent changes to the European Pharmacopoeia chapter for water for injection. So today's agenda, I'll give, first of all, I'll give a little bit of history behind the changes to the European chapter for water for injection. Take a look at some of the challenges in moving from production of water for injection using a still to using reverse osmosis. Touch on the increasing importance of total organic carbon and conductivity monitoring in these water systems. There's a small section on a TOC measurement itself, what TOC is and how it works. And then I have a section on best practice for calibrating TOC and conductivity analyzers. And then there's a section on support for water system TOC excursion root cause investigations, a section on a method for detecting changes in water system organic chemistry, and then I'll bring it all together in a conclusion at the end. So first of all, let's take a look at some of the history behind the changes, this recent change, to the European Pharmacopoeia. Although much work's been done over the last decade to harmonise the pharmacopoeias across the world, the European Pharmacopoeia chapter on water for injection stood out because it specifically called for the use of a still for the manufacture of water for injection. Other pharmacopoeias merely listed the key quality parameters of water for injection, which are TOC, conductivity, microbial colony forming units, and endotoxin levels. However, with pressure to reduce carbon footprints and reduce manufacturing overheads, representatives from the United States Pharmacopoeia, the European Pharmacopoeia, and the Japanese Pharmacopoeia came together to survey the pharmaceutical industry regarding the quality of water manufactured by reverse osmosis and, in particular, the level of control these water treatment plants had over microbial colony forming units. During the period from 2004 to 2010, the JP, USP, and EP gathered surveys on water for injection from reverse osmosis from across the world. And the results were surprisingly good, with many studies showing an excellent water quality, matching water for injection standards, and with very good levels of microbial colony forming unit control. In 2011, an expert workshop was formed with representation from the pharmaceutical manufacturing industry to consider changing the European chapter on water for injection to allow the use of reverse osmosis as long as the water produced that way met the key quality attributes of water for injection and showed high levels of control. And finally, in 2016, the new chapter for water for injection in the European Pharmacopoeia was adopted, allowing for the first time the use of reverse osmosis for the production of water for injection. However, certain challenges exist for those who are wishing to change their water production process from a still over to reverse osmosis. There are three main drivers for the industry to move from stills to reverse osmosis. Manufacturers are, of course, under pressure to meet the reduction in carbon footprint and energy consumption set in the climate change agreements. And at the same time, the loss of patent protection and increasing global competition means that companies need to reduce their operating overheads in order to remain competitive on a global scale. And finally, many have recognized that heat sterilization of water systems only controls the microbial levels and biofilm buildup, and that alternative treatments such as ozone cannot actually offer improved microbial sanitization and biofilm control if they're used correctly. Producing water for injection using a still is a very energy-consuming process. The still itself uses vast amounts of energy to heat the purified water until it turns into steam. The steam is then condensed to form water for injection. As the water for injection is made hot, it's transferred into the storage vessel and distribution system hot as well. To discourage microbial buildup in the storage tank and the distribution lump, they're both kept hot. Although the storage vessels vary in size, commonly in a large manufacturing facility, they contain thousands of liters of water, and this must be heated and maintained at temperatures higher than 65 degrees centigrade to prevent microbial excursions. Points of use that require cool or cold water, either for the process reasons or for the safety of the personnel, they have to have the water cooled using heat exchangers, which again consume energy. And as the points of use are effectively small loops in themselves, any water that's not used circulates back into the distribution loop, and this has to be reheated back up to above 65 degrees centigrade before it enters the loop. Periodically, the water in the storage tank and distribution loop has to be heated up to temperatures higher than 80 degrees centigrade to hold back the formation of biofilm inside the pipework. Heat sterilization of water systems tends to control the proliferation of biofilm and microbial contamination. Microbes living in a heat sanitized water system are generally unable to replicate to form a colony, and hence the term commonly heard these days about viable but non-culturable. Ozone sanitization, however, actively oxidizes the organic material in the water, including the microbes themselves, and removes life and its source of nourishment from the water system if used correctly, and leading to true sanitization of the water system. Biofilm can build in heat sterilized systems, and though it's kept under control by frequent heat sterilization, its presence can form a challenge when switching from an established heat sterilized system over to ambient water manufacturing using reverse osmosis. So let's take a brief look at the alternative systems proposed for water injection production using the reverse osmosis and ozone. Under normal conditions, the osmotic pressure across a water-permeable membrane causes the water to pass through the membrane to the side with the highest concentration of salts. Reverse osmosis, as the name suggests, reverses the direction of the water flow by pressurizing the incoming water side of the membrane so that clean water is pushed through the membrane, leaving the contamination that was present on the water behind. Water made through the reverse osmosis process is manufactured at ambient temperature and does not require high energy input to heat it. A study done by a working group from the pharmaceutical industry and water system suppliers under the auspices of the International Society for Pharmaceutical Engineering, the ISPE, resulted in the publication in 2012 of the ISPE Guide on Ozone Sanitization of Pharmaceutical Water Systems, which recommends the advantages of ozone sanitization and lays down best practices. Typically, ozone is generated by electrolysis of the water itself in the loop and injected into the return leg of the water loop. Because the ozone is generated from the water itself, there's no risk of contaminating the water systems. Levels of ozone are maintained at all times in the storage tank, so as the water is circulated through the tank, it is sanitized. Excuse me. As the ozone is considered an added substance, it must be removed before the water is used. And this is achieved using an ultraviolet light, which is an ozone destruct system in the water loop itself. And as the water leaves the storage tank, it's destroyed using the UV light. Ozone breaks down very rapidly in the presence of UV light and is prevented from entering the water loop. Periodically, when the water system is not being used by production, the UV destruct light is turned off, allowing ozonated water to circulate throughout the entire loop. The ozone destroys both microbial contamination and any biofilm that's been built up inside the pipework. If a water injection system is quite old, there's a very real possibility of biofilm buildup. Microbes can live in the biofilm in an oleotrophic state without being detected. A common error when retrofitting an ozone sanitized reverse osmosis plant to such a water system is not allowing for a suitable time period to allow the water system to come back under control. When first applied, the ozone will start to break down the surface of the biofilm, oxidizing the organic materials to form carbon dioxide. And this carbon dioxide dissolves in the water and elevates the conductivity. So we're going to have spikes of TOC and elevated conductivity. Secondly, as the biofilm is broken down, organic material will slough off the inside of the pipe and elevate the TOC levels in the water. With elevated levels of organic material in the water and a return to ambient temperatures, microbes present in the biofilm may start to proliferate, causing elevated microbial count in the water until the ozone does its job and destroys the microbes too. Eventually, as the ozone destroys all the biofilm and the TOC in the water, the loop will return back to normal control and can be used for normal operation. So let's take a look at the importance or increasing importance of TOC in these new reverse osmosis water for injection systems. In September of 2004, the FDA issued their process analytical technology guidance, encouraging the pharmaceutical industry to change their bias on final product testing and employ more online process monitoring analyzers in an attempt to get a better process understanding and better process control, leading to improved right first time results. Online monitoring, particularly for TOC and conductivity, have taken on an even greater significance since the European Pharmacopoeia adopted its revised monograph on water for injection in March of 2016, allowing for the first time the generation of water for injection from reverse osmosis. The working group responsible for advising the European Directorate on their new water injection monograph gave a warning that reverse osmosis may not be as robust as stills, and they encouraged a focus on online TOC and conductivity monitoring as early warning of potential RO reverse osmosis integrity breaches. So let's take a look at total organic carbon, just what it is and how it's measured. The FDA mandates 4 critical water quality attributes: monitoring for inorganic contaminants using conductivity, monitoring for TOC, monitoring for endotoxins, and microbial colony forming units. As I mentioned earlier, the FDA encourage online process monitoring for quality control in their Process Analytical Technologies, or PAT, initiative. But at the same time, the expectations for the amount of quality information is increasing, and in many cases, the responsibility for collecting this data is passing to relatively unskilled production staff. A recent report indicated that 79% of the FDA's 483 warning letters issued in 2016 to the pharmaceutical industry, they cite data integrity as an issue. Poor data integrity may lead the FDA to call for a product recall. Total organic carbon is a non-specific test, i.e. the results of TOC analysis can tell you the levels of organic carbon in the water, but it cannot tell you exactly what those organic substances are. TOC is a measurement of the mass of carbon atoms present in organic material in the water, reporting TOC in units of mass per litre of water, i.e. micrograms per litre, or more frequently expressed as parts per billion. The carbon atoms are released from the organic molecule by breaking the molecule down through the process of oxidation. The carbon forms into carbon dioxide, which in turn dissolves into the water to elevate the water's conductivity. Before the TOC is measured, the TOC analyzer must first measure the amount of carbon dioxide dissolved in the water already, and this is called total inorganic carbon. Then the organics present in the water are oxidized to release the carbon they contain, and total carbon is measured. By subtracting total inorganic carbon from total carbon, the levels of total organic carbon in the water can be ascertained. In the European Pharmacopoeia chapter on TOC, it emphasizes the importance of ensuring the complete oxidation of the organic molecules to ensure that all organic carbon is released and measured accurately. Most TOC analyzers used to monitor pharmaceutical grade water use ultraviolet light to oxidize the organic materials, releasing the carbon atoms in the form of carbon dioxide. Carbon dioxide dissolves into the water, elevating the conductivity, and it's this change in conductivity is measured by the TOC analyzer and used to calculate the amount of organic carbon present in the water. The problem is that as complex long-chain molecules are broken down during the oxidation process, they may form organic acids, which contribute more strongly to the water conductivity than the final carbon dioxide does. If the TOC analyzer does not complete the oxidation of the organic molecule, one of two things may happen. Either the carbon remains bound up in the organic and cannot be measured, so the TOC is actually underreported, or the TOC analyzer takes a conductivity measurement before complete oxidation when the organic acid is present and overreports the amount of TOC in the water. Either way, assuring complete oxidation is the only way to measure TOC accurately. As these TOC analyzers are in fact use conductivity to measure the TOC, it's attractive to use them to measure both TOC and conductivity. However, the Pharmacopoeias insist on two calibration steps for conductivity analyzers. The first one is to make sure you can measure the cell constant of the conductivity analyzer using a certified traceable solution. And the second one is to check the accuracy of the conductivity meter electronics using an external certified resistor. So if TOC analyzers and conductivity analyzers are to provide accurate indication of the health of the water system, they must be calibrated correctly. So in this section, we'll take a look at best practice for calibration of these analyzers. There are two types of calibration. The International Standards Organization, ISO, defines calibration as a validation of an instrument against a known certified calibration standard. If the measurement error is not acceptable when compared to these standards, then a calibration adjustment must be undertaken to adjust the instrument's calibration slope to bring its performance within acceptable tolerances. When calibrating an instrument, best practice dictates that the current performance of the instrument be checked before any adjustment is made. This as-found calibration confirms that the instrument has been working within acceptable tolerances in the period of use. Then the instrument calibration should be fine-tuned to adjust it so that it reads as close to the certified standard values as possible to avoid long-term calibration drift. Having made this adjustment, calibration should be checked once more, validated against certified standards to make sure that the adjustment has left the instrument working accurately. Now, there are 21 CFR Part 11 issues with the typical instrument calibration and system suitability testing, with many manual SOP steps to be followed in the typical water monitoring process. Values for certified standards used in the calibration process are manually typed into the TOC analyzer for both calibration and system suitability, inviting human error and mistyping. Pass-fail reports have to be manually calculated, and finally the electronic record is created by photocopying the manual calculations and manually typing the results into the system, and all of these steps can be prone to human error, leading to 21 CFR Part 11 integrity issues. Now, if we're to rely on the TOC analyzers to provide accurate information to support batch release data, then there are some significant issues to consider. As I discussed earlier, pharmaceutical-grade TOC analyzers rely on ultraviolet light to oxidize the organic molecule to release the carbon dioxide for TOC analysis. Total carbon minus total inorganic carbon equals total organic carbon. However, as the UV lamp inside the TOC analyzer ages, the intensity of UV light output reduces, and this can result in poor TOC analysis. and certainly in TOC analyzers with continuous flow and fixed oxidization time. Should the UV lamp fail completely in the TOC analyzer, then it will be unable to oxidize the organic molecule and free the carbon atoms. So we will be unable to measure TOC at all. In a modern water treatment system with low TOC levels between 5 and 10 parts per billion, a UV light failure may go undetected, and the user runs the risk of releasing products onto the market without accurate TOC analysis results, especially as an out-of-specification TOC excursion would go undetected during the time period before the UV lamp is replaced. Naturally, any TOC or conductivity excursion would lead to a root cause investigation. The problem is that TOC excursions can often be short, transient events, detected by the TOC analyzer, but disappearing by the time the team comes to take the water samples for root cause investigation. As stated earlier, 1 part per billion of carbon is equivalent to 1 microgram per liter of carbon in a liter of water. So let's take a look at a typical situation. In this modern water injection system on the screen here, the TOC levels are commonly recorded around 26 parts per billion. Suddenly, a slug of TOC is fed into the water system by accident from one of the points of use, causing excursions of 750 parts per billion on all the other points of use, equivalent to 750 micrograms per liter of water. This is detected and reported by the online TOC analyzer. The 750 micrograms per liter of carbon now enters the water for injection storage tank, which in our example contains 1,000 liters of water for injection. The 750 milligrams of carbon is now diluted in that 1,000 liters of water and becomes just 0.75 micrograms per liter, or 0.75 parts per billion. This diluted carbon is very easily destroyed by the UV lamp commonly used for microbial control on water injection systems, as the water passes back out from the storage tank into the distribution loop. Now TOC levels in the loop return to their safe low TOC value, but it's too late because during the excursion the levels of TOC at the points of use was outside the pharmacopoeial limits, and any batches being manufactured at that time cannot be released into the market. What makes the situation worse is there's no way to carry out root cause investigation analysis to find the likely sources of the TOC excursion, as all the evidence has been effectively destroyed and diluted in the water storage tank and using the UV lamp. So there's no way to put preventative action in place to stop the recurrence of the excursion again at a later date, thus compromising future batches of product as well. So we've learned that the European Pharmacopoeia has paved the way for companies to reduce their carbon footprint, reducing their energy overheads, and be in a better place to compete globally by allowing water for injection generation by reverse osmosis. However, we've also seen that the expert committee advising the European Pharmacopoeia warned that reverse osmosis may not be as robust, and they recommended increased focus on TOC and conductivity analysis as a first indicator that the reverse osmosis integrity may be becoming compromised. So now let's take a look at what else may help warn us about possible compromises in our water for injection generation system. Monitoring the TOC level itself may give us sufficient information but one other indicator that things may be going wrong is a change to the type of organic contaminant present in the water. TOC analyzers that can report a change in the oxidation profile of the organic in the water may actually help us spot when things are starting to go wrong in time for us to take action before an excursion appears. An elevation in TOC levels combined with a change in the oxidation profile of the organic may well hint that not only are the TOC levels creeping up, but the type of organic getting into the water system has changed as well, leading us to carry out more in-depth water grab sample analysis to check what might be going wrong. So we've learned that TOC and conductivity analyzers can be strong allies to help us keep our water systems under control. We've learned how calibration is important and how complete oxidation is recommended in the European Pharmacopoeia for complete and accurate TOC analysis. So let's take a look now as to how the PAT700 TOC and conductivity analyzer can help support you through the challenges of moving to water for injection production, moving from using reverse osmosis. In the PAT700, 21 CFR Part 11 issues are removed as all calibration and system suitability SOPs are built in and automated. There's no manual data entry and no manual calculations. Calibration and system suitability standards certified values are contained in an RFID tag in the base of the standards bottle. This data is read by the PAT700 when the standards are placed into the calibration bay, thus eliminating manual entry and eliminating manual data entry. At the same time, the PAT700 checks that the standards are still in date and they're actually inserted in the correct order in the calibration bay. The PAT700 is unique in that it has two auto-switching main and standby UV lamps. It monitors the UV lamp light output, and should the main UV lamp fail, it automatically switches the standby lamp on and sets an alarm to warn the user that the UV lamp requires changing at the next service. Not only is this analyzer compliant for TOC requirements, but it can also be fully calibrated to USP requirements as a conductivity meter too. The cell constant can be checked using a certified conductivity solution, and the meter accuracy can be verified against a resistor of known certified value. The ANATEL PAT700 ensures complete oxidation every time. Initially, the conductivity of the water sample is measured to establish the quantity of baseline total inorganic carbon. Then the ultraviolet light is turned on. The PAT700 monitors the change in conductivity as the organic molecules are oxidized to carbon dioxide. And when there's no further changes in the conductivity, the analyzer measures the new conductivity and compares it with the baseline total inorganic carbon conductivity. The difference in conductivity is directly proportional to the amount of organic material trapped in the water sample. As mentioned earlier in the presentation, TOC excursions can frequently be very short transient events. So the PAT700 supports root cause investigation into these TOC excursions by capturing a sample of the TOC excursion into an empty excursion bottle, which is preloaded in the calibration bay. This can then be taken to the QC lab for root cause investigation to identify the possible sources of the contamination, hence supporting corrective action and preventative action CAPA. So to summarize, the PAT700 TOC and conductivity analyzer from Beckman Coulter is designed to be robust with all necessary SOPs built in and automated. There's no manual data entry or calculations, and uptime is maximized by having auto-switching main and standby UV lamps. There's a 12-month service interval and calibration interval, and it needs no reagents. It is designed to be fully compliant for both TOC and conductivity. As it ensures complete oxidation to get accurate TOC results every time. It captures a sample of any excursions, so that can support root cause investigations, and it uses Microsoft's Active Directory controls for username and password, giving complete compliance to 21 CFR Part 11. So that concludes my talk today. I believe you should have just received a poll inviting you to download my white paper on this topic, which has more information. As I say, that concludes my presentation today. So thank you very much for listening. If there are any questions, then I'd be happy to take them.
Thank you so much, Tony, for your presentation and for your important research. We will now start the live Q&A portion of this webinar. If you have any questions, audience members, that you'd like to ask, please do so now. Just click on the green Q&A button at the lower left of your presentation window. Type those questions into the box that appear on the screen and click the send button. We'll answer as many as we have time for. So let's get started. We have a great audience today and some wonderful questions already coming in. Our first question, Tony, is if TOC excursions can be transient events, how can a proper root cause investigation be carried out? Audience members, I think he might have his presentation microphone.
Sorry.
There he is.
Sorry, that's my fault.
There's Tony.
There I am. Sorry.
Okay. Do you want me to repeat the question?
No, that's great. Sorry, I was on mute. Yes, so yeah, you're quite right. TOC events, they are often very short-lived, transient events. So, and of course, to get to root cause, it's important to capture a sample of that water whilst the TOC excursion is happening, in order to establish where the TOC spike may have come from. And that's why the PAT 700 from Beckman Coulter captures a sample of that water whilst the TOC event is actually happening.
Thank you for that. Our next question is, if the Pharmacopoeias mandate the system suitability test as a requirement for TOC analyzers, why is a separate calibration procedure required?
Yeah, it's a good question, and often system suitability confuses people. In fact, system suitability is not a calibration. It merely establishes that the TOC analyzer is capable of oxidizing the relatively difficult to oxidize substance benzoquinone, as well as it can oxidize the more easily oxidized sucrose. A calibration adjustment, however, adjusts the analyzer measurement slope to give the best results when compared to certified TOC standards. And a 3-point calibration could also establish that the measurement slope is linear. And the PAT 700 automates both system suitability and calibration and calculates the pass-fail results and the linearity of the analyzer's measurement slope.
Great, thank you. And I want to thank our audience members for their questions. We do have one more coming in, and we encourage others to continue to write. Our next question is, in a TOC analyzer, using UV light to oxidize the TOC for analysis, what happens if the UV light starts to fade?
Sure. Well, the UV light is critical to the analysis. And in fact, in most TOC analyzers, the UV light output is not monitored directly. So when a UV lamp starts to age and its output starts to drop off, then the TOC analyzer will no longer be oxidizing correctly, and the analyzer will underreport. And for this reason, the PAT 700 directly monitors the UV lamp output and automatically switches to a standby UV lamp should the main lamp begin to fail.
Thank you. And thank you, audience members, for your participation. Tony, did you want to close with any remarks to the audience to kind of wrap this presentation up for them? Oh, and actually, one more question just came in. Do you want me to go ahead and ask you that question?
Yes, please.
Okay, we have, can the TOC readings be used to trend endotoxin levels?
That would be nice, wouldn't it? What a nice idea. Sadly, no, because it's not a specific test. TOC analysis is just an indication of how much organic carbon there is there. It can't actually tell you whether it's an endotoxin or not. However, as I've mentioned, if you see a change to the TOC levels combined with a change of the oxidation profile, which the PAT 700 will report to you, it will tell you if there's been a change in the oxidation profile. That's a good indication that there's a change to the organic chemistry in the water system, and certainly an indication that more in-depth investigation could be required.
Wonderful. Thank you so much. Tony, did you want to wrap up your presentation with any closing remarks for our audience members today?
Just to say thank you to everybody for listening today, and thank you for the questions. It's been a good interactive session.
Thank you, Tony, and thank you for your important research. I'd also like to thank LabRoots and our sponsor, Beckman Coulter, for making today's educational webcast possible. Before I go, I want to let everyone know that today's webcast will be available for on-demand viewing through April 2018. You'll receive an email from LabRoots letting you know when the webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's live event. That's all for now, and thanks for joining us. We hope to see you again soon. Bye-bye.
Bye-bye.